Welcome to today's deep dive. I am your host, and I'm here with our resident expert. Today, we are exploring a high-level mechanical engineering glossary.
It's focused specifically on precision transmission, and we're sourcing this all from a technical slide deck.
Right, and just as a quick disclaimer for you listening, we are just sharing the concepts exactly as they are presented in this source material. We're not taking any sides in any engineering debates or, endorsing specific methods. We are just here to unpack the ideas.
Exactly. And the original deck actually breaks these concepts down bilingually for international engineering teams. But for our deep dive today, we're going to focus entirely on unlocking the physical impacts.
So the physical impacts and the R&D applications, because, these aren't just vocabulary words, right? They are essentially the secret recipes for making machines perfectly precise and, well, virtually indestructible.
They really are. And building an indestructible transmission is actually a massive physical paradox.
Wait, how so?
Well, you're trying to push metal past its natural failure point without destroying it in the process. To make a gear survive millions of cycles under huge loads, you have to harden it with extreme heat.
Okay, makes sense.
But extreme heat warps the precise microscopic geometry you literally just spent hours cutting.
Ah, right. It's a total catch-22. So how do engineers actually cheat that?
So the classic solution to surface hardness is carburizing. But that high heat introduces, unacceptable dimensional distortion for something like a precision internal ring gear.
Yeah, you can't have a warped gear.
Exactly. Which is where a process like nitriding comes in. It operates at a low temperature, diffusing nitrogen directly into the metal's crystal lattice.
Without melting it.
Right, without crossing the phase transformation threshold to the steel.
So it's kind of like hardening a cake without letting it expand or lose its shape in the oven.
That's a great analogy, actually.
Yeah.
Yeah, you get the boosted wear resistance and fatigue life,
Yeah.
but the gear retains its exact manufactured shape.
Okay, but nitriding only gets you so far, right? Before you introduce friction issues.
Right. For components rotating at extreme speeds, like sun gears, you hit a thermal wall. And that's why you see the application of DLC, or diamond-like carbon coatings.
Diamond-like carbon, that sounds pretty intense.
It is. You're layering a thin carbon film that relies on a very specific structural mechanism. It mixes sp2 graphite-like bonds, which provide ultra-low friction, and sp3 diamond-like bonds, which deliver extreme hardness.
Wow, so it is essentially giving the gear a permanent, frictionless suit of armor?
Precisely. By minimizing the heat generation right at the source, the DLC coating allows those high-stress sun gears to approach a basically maintenance-free life cycle.
That is wild. But, okay, so once you've hardened these surfaces, you hit another wall. How do you physically polish the deep roots of an internal gear tooth or like a complex internal cavity where standard cutting tools physically cannot fit?
Yeah, you have to abandon rigid tools entirely and move to fluid dynamics. The deck introduces abrasive flow machining, or AFM, right? It forces a pressurized, semi-fluid abrasive right through the part. The key here is the fluid's rheology. As the passage narrows, say, inside a microscopic crosshole, the fluid actually becomes more viscous and highly abrasive right at that bottleneck.
Wait, really? So it's essentially power washing the inside of a microscopic maze with liquid sandpaper?
That is exactly what it's doing. It guarantees a uniform polish precisely in the areas that are the hardest to reach.
Now, contrast that fluid approach with the brute force of cutting tough metals, like titanium carriers. Doesn't the friction there generate massive localized heat?
It does, which leads to work hardening. And that essentially ruins the machinability of the metal.
So how do they get around that?
The source points to cryogenic machining. By flooding the cutting zone with a medium like liquid nitrogen, you prevent that heat damage entirely.
Liquid nitrogen, just blasted right on the cutting zone.
Yeah, the extreme cold stops the localized phase changes that cause work hardening. It leaves a pristine surface finish without degrading the material's underlying structural integrity.
Incredible. Which brings us to the final hurdle in the manufacturing sequence. We typically think of finishing a surface by removing material, cutting, grinding, polishing. But the deck talks about roller burnishing.
Right, where you're relying on plastic deformation instead, by using heavy rollers to literally crush the microscopic peaks of solid metal.
But wait, if you're crushing metal with heavy rollers, aren't you risking subsurface microfractures if the roller pressure is too high?
You absolutely are, which is why the pressure load has to be calculated flawlessly. When calibrated correctly, compressing those microscopic peaks into the valleys alters the crystal lattice structure.
Oh, by increasing the dislocation density.
Exactly. That localized compression is exactly why the surface gets significantly harder. It yields a highly smooth, high-strength bearing surface, perfectly suited for high-stress areas like output shaft feeds.
And all without removing a single atom of material.
It's not one.
Wow. So what does this all mean for you when looking at high-level mechanical design? Whether it's manipulating phase changes with low-temperature diffusion, or tuning fluid rheology to polish hidden geometries, or restructuring the crystal lattice with sheer pressure modern precision engineering is just an absolute masterclass in outsmarting physics.
It really is.
Yeah.
Every technique we've discussed is a way of bypassing the natural degradation of materials under friction and thermal load.
It definitely makes you wonder, though, with techniques like DLC coatings and cryogenic machining pushing friction, heat, and wear closer and closer to absolute zero, what is the ultimate physical limit of mechanical longevity?
That is the big question.
Right, like, will we eventually create a purely frictionless machine? It's the ultimate engineering holy grail, and definitely something for you to ponder the next time you turn a key and let thousands of precisely hardened parts go to war. Thanks for joining our deep dive today.